everyone. Welcome to week 5 of the chemistry tutoring sessions. I will be going over chapter 10 and chapter 11 today. And as you probably saw in the email, we will be going over heating curves and some solutions, as well as working with pressures and molar masses and all of that jazz. So let's get started on question 30. Hopefully you can see my screen okay. Okay, we will be going over question 30 like I was saying. And we have the question reading. Heat is added to boiling water. Explain why the temperature of the boiling water does not change and what does change. So I will write this down as I say it, but the reason why boiling water, or the boiling water's temperature, does not change is because all of the energy is going to be putting into the water to change the phase, so from a water to a gas, so it can't change temperature yet because all that energy is being used towards changing the phase, like I was saying, so liquid to gas, and that's basically what is changing, and what's not changing is the temperature, like it was stated. Does not change is the temperature because the energy is being put into changing the state. So liquid to gas. And so that's kind of the baseline for starting today of, when you put energy into something, first it needs to change the phase, and then you can actually change the temperature. So now let's get into something of a calculation problem. So this one reads, carbon tetrachloride, CCl4, was once used as a dry cleaning solvent, but is no longer used because it is carcinogenic. At 57.8 degrees Celsius, the vapor pressure of CCl4 is 54.0 kilopascals, and its enthalpy of vaporization is 33.05 kilojoules per mole. Use this information to estimate the normal boiling point of CCl4. Okay, so this is asking the normal boiling point for this compound, CCl4. And at normal boiling point, it's important to note at normal boiling point, the temperature for vapor pressure has to be equal to atmospheric pressure. So this will be a value that we are pulling that will match the atmospheric pressure, and the atmospheric pressure in kilopascals, since it uses that unit, is going to be 101.325 kilopascals. And so we will be using the formula natural log P2 over P1, so those are the two different pressures at two different times, equal to enthalpy of vaporization divided by an R constant multiplied by the difference of the inverse of the temperatures. Sorry, T1 and T2. So we know we are using this equation right now because it is talking about the change in temperature, the change in pressure, and also it's using, something is changing in the vapor pressure. So we know that we're going to be using all these values. So it's a good indicator because it matches all of the things that we're going to be using in this equation. So to start off, we need to kind of figure out what is P2, what is P1, what is T1, what is T2. So looking at the problem here, it said that at 57.8 degrees Celsius, the vapor pressure is at 54. So that is going to be the T1 and P1 value. But always remember that when you're working with temperature, it's in Kelvin. So we can do a quick conversion for that later. And then it also gives us the enthalpy of vaporization. And we know that P2 needs to be this value that we just came up with because it's asking for normal boiling point, which is going to be the atmospheric pressure. So that is P2. So the only unknown for this is going to be the T2, the boiling point. So that is the temperature that we're going to find. And what I always like to do with these kinds of problems is first, before adding any of these values in yet, to solve for whatever I'm trying to find, so just move things around. So I'm going to move things around to solve for T2. So to solve for T2, I can multiply both sides by R, and I'm just going to switch it first, so the enthalpy will be over here. Just to make it a little bit easier. Okay, now I can multiply both sides by R, so we'll get R ln P2 over P1, and then I can divide both sides by the vapor pressure. And once this one will get crossed out, then I can minus this inverse of 1 over T1. And what will be left is 1 over T2, if you saw what I did there. So there's going to be a negative here, and it's also inverse, so to get rid of that, we multiply both sides by a negative. And since there's an inverse, we can just multiply this entire term by -1, so that will switch it around for us already. So now we will be left to solve for T2. If you want me to go over that a little bit slower, I can, but yeah, you can always go faster or slower depending on how quick your mind works with solving for different terms. Okay, but now we have the equation that we're going to be working with, and our R value, I forgot to mention, is going to be, let's see, 8.3145 times 10 to the -3rd joules per mole K. Okay, so that is the R value. So now we can just plug in all of our values and solve for T2. So like I said before, our R value is 8.3145 times 10 to the -3rd natural log of P2, which is going to be the P2 in our problem, which is the atmospheric pressure. And then the P1 that we have is going to be 54 from the problem, because that is what it is at first. And then divide this whole thing by the enthalpy value, which is going to be 33.05. And then the T1 is going to be 330.95. And the reason why it's that value is because it gave us 57.8, and then we add 273 to it to get it into Kelvin. And so multiplying all of that out, we will get a value of 349.25 Kelvin. Or when you subtract the Kelvin conversion, it will also be 76.10 degrees Celsius. So that is the answer for this one. Basically, you just want to keep track of what's what, and it's easier to solve for whatever you're trying to find in the very beginning before you add in all your values and then move things around. I think that's one of the easier things to do. Okay, now that we have solved 38, let's move on to the next problem. Problem 51. Okay, so 51 says, how much heat is required to convert 422 grams of liquid water at 23.5 degrees Celsius into steam at 150 degrees Celsius? So what I recommend doing to start off with these kinds of problems is first make a phase diagram to figure out what terms I need to calculate the energy for. Because we're working with the equation of Q equals MCAT or Q equals the enthalpy value if you're changing a phase plus the number of moles. So these are the two kinds of terms that we could be working in this problem. So let's first write down the phase diagram and figure out what this kind of looks like. Okay, so it's going to be water at 23.5 degrees Celsius. So it's going to be in the liquid stage because it's between 0 and 100. So we're at the liquid stage here. And it needs to go into the gas phase, so we'll have a changing of a phase, and then we need to heat it from 100 degrees to 150. So we're going to have three different terms of changing this water into a hotter gas, vapor. So let's write down what all those terms will be for the total amount of heat we're putting into this. And because it's going to be heating up, it'll be a positive energy value because we have to put energy into the system to change and heat what we're working with. So Q in this problem will be equal to MCAT of heating up the water. So I'm going to say WW, so warm water. So WW will be warm water. And later on I'll put a term for warming of the gas, so WG. So it'll be Q equals MCAT WW, and then we'll need to change the phase from liquid to gas. So that will have to have the enthalpy of gas vapor. So I'm going to say gas right here, times the amount of moles. And then we'll need another term because we have to heat up this gas to another temperature. So we'll have another MCAT of WG, and those are all three terms that we're working with here. Like I said, it's important to look at the diagram and figure out how many things are going on in changing it, and setting it equal to, if we're finding out how much is happening, set it equal to Q, or if it's in an enclosed system, sometimes you set it equal to 0 because they're transferring to each other. But in this case, we're figuring out the total thing, what's going to happen, so we set it equal to Q. So let's first work on the first term here. It is MCAT, and whenever you're finding the C value, you have to find it for the water value. And same with over here, the C value for WG. This needs to be for the gas value. So just keep that in mind, that specific heats will be different for a different phase. So the mass is going to be 422, what it gives in the problem. Actually, I'm going to move things off to the side really quickly. Let's cut that so we have more space. Okay. Because I know this is going to be a longer problem to write out. Okay, so we have the the amount of grams of the mass here. So that's 422 grams. And then the C value for water is going to be 0.00418. And that's going to be in joules per gram Celsius. You might have seen the C value as 4.18. That's going to be in kilojoules. So I already made the conversion from kilojoules to joules. So that's the value that we're working with here. And then the change in temperature is going to be what we're starting with, right? That's going to be the initial value. So it's going to be 100 minus 23.5, the final minus initial, because we're still in the liquid phase here, so it's going from what we're starting with, and we can't go beyond 100 because it's still in the warming. The next term is when we can actually change the phase. Okay, so we're done with this term here, and so now we're going to add the second term, which is going to be the enthalpy times the moles of the water. So the enthalpy value of water is going at vaporization is 40.67, and that's in, I believe, kilojoules. So we'll have to convert that. No, that's already in joules. Yeah, 67 joules per mole. And to get it into moles, we'll do a molar mass conversion. So that is going to be the mass that we started with, which is 422. And the molar mass of water is 1 mole over 18.02 grams. So after we multiply that out, we'll be left with moles. And so now we're done with the second term here. And so now let's work on the third. So then the last term will be the mass of the water, so 422 again, times the C value, but this time we're working with gas. So it's going to be 0.00186. And let me make this a little bit smaller. Hopefully you can see this okay. And multiplied by the change in temperature as well. And so since we're starting with 100 degrees Celsius here, and we're changing it to 150, it'll be 150 minus 100 for our change in temperature. So those are all the terms written out. So now all we have to do is just run this in our calculator, and I already did this earlier, but the first term will be a positive 134.94. The second term will be 952.43, and the third one will be 39.24 or 25. And what's really interesting here when you look at each of these terms, the first one is warming the water, so that is the joule amount of warming the water. The second term is the joule amount of changing the phase from liquid to gas. And then the third one is heating up the steam, or the gas. So it's interesting that the second term is really the bulk of the energy, because it takes a lot more energy to change the state, more so than warming up the liquid or the gas, which is interesting. But the final answer will be 1027 and kilojoules. Oh, sorry, before, this is in kilojoules, not joules. And so that is our answer for 51. If you don't have any questions, I will move on to the next one. So this one says, predict whether each of the following substances would be more soluble in water, a polar solvent, or in a hydrocarbon such as heptene, a nonpolar solvent. So the first one is vegetable oil, and it is nonpolar. And whenever we have a nonpolar substance, it likes to be with nonpolar things as well, because it's very balanced. It doesn't like to mix with polar things because it repels away from it because of it. So the vegetable oil, since it's nonpolar, it will like to be in the nonpolar solvent. So heptene. And let's move on to B. So B is isopropyl alcohol, and it is polar, so it also likes to be with the polar compound, and that is water in this case. So it likes to be with water, because polar things like to be with polar things because of that partial positive, partial negative. It will like to be with whatever is opposite to it. So the partial end, or the partial positive of the isopropyl alcohol, will like to bond with the partial negative of water, which is oxygen. So it likes that opposite attract partial charge that is happening. And so the last one is potassium bromide, and it is ionic. So with ionic compounds, it is going to be in its ion form when it's mixed with the other solvent. And so since the ions have charges on itself, it will like to be with the other polar charges that is happening. So it'll like to be in the polar solvent, which is water, because the ions itself have charges, and they'll like to bond with those, or temporarily bond with those things and be attracted to it. Okay, let's move on to 11. And let me know if you can hear me okay as well. Okay. So this one says, consider the solutions presented. Which of the following sketches best represents the ions in a solution of iron nitrate aqueous? So in this compound, we have iron and we have 3 nitrates. And because it is aqueous and because it will go in ions in solution, what we will see is the nitrates by itself and the irons by itself, because it will be ions. It'll split apart from each other in the solution, so it will not be bonded anymore. So the picture that best describes that is going to be Z, because we have the irons by itself and we have the nitrates by itself. Okay. And now it says, write a balanced chemical equation showing the products of the dissolution of iron nitrate. So we will first start off with the iron nitrate, because that is the first thing that we have. And like I was saying, it is going to be aqueous and it'll be in its ionic or ions in this solution. So what will happen is we will have an iron by itself as 3 plus. And because we know this, or we know the iron is 3 plus, iron can sometimes be 2 plus or even 4 plus, but we know it's 3 plus because the NO3 itself is a minus charge, and because there are 3 of them, it's going to be 3 minus, and we need a 3 plus to balance this out. And so this will be aqueous, and this will also be aqueous. And what we're starting off with was actually a solid, but it broke apart in the solution. So that is how you write the balanced chemical equation for that one. So now let's move on to 19. 19 says, calculate the percent by mass of KBr in a saturated solution of KBr in water at 10 degrees Celsius. See figure 11.16. This is figure 11.16. And so now we need to report the percentages to one significant digit after we find that. So looking at this graph here, it said we need to be at 10 degrees Celsius. So looking at the bottom axis, which is temperature, it looks to me like 10 degrees will be right here on that line. And we're finding KBr, which is going to be right here. Oh, if I can draw straight. So it's going to be right there. That's the KBr line. And so crossing over to the solubility, it looks like we will get a value of around 60 for our solubility. And the solubility units says right here that it's grams of solute per 100 grams of water. And so now we have all that we need to figure out the percent by mass. So the percent by mass equation is going to be the mass of solute over the mass of the solution. So that's the solute and the solvent. And we also multiply it by 100 because it is a percent. And so to calculate for that, the mass of the solute, like I said, was 60 for the solubility. So that was 60 grams of the KBr. So that's our solute. And then the mass of the solution is going to be the 60 of the solute. And the water here is the solvent. So 60 plus the 100 grams of the solvent is going to be our total mass of the solution. And then times that by 100. So that's going to be 60 over 160. And we will get a value of around 40%. and so that is percent by mass. And that's how we solve that one. Okay, so let's move on to the next problem here. So 21 says at 0 degrees Celsius and 1.00 atmospheres, as much as 0.70 grams of O2 can dissolve in 1 liter of water. At 0 degrees Celsius and 4 atmospheres, how many grams of O2 dissolve in 1 liter of water? Okay, so we're going to be using this equation here before we figure out what our terms mean. Solubility equals KH times P. So we don't know our KH value yet, but we know that we're working with the same kind of compound. So right now we're working with O2, a gas. So we have to figure out this KH value first, and then for the beginning portion of this problem, and then we can figure out later for a different scenario using the same KH value, we will find out how many grams have dissolved. So basically, let's figure out the KH first. So we have solubility divided by P. And so the solubility in this problem, it said that 0.70 grams can dissolve in 1 liter of water. And so solubility is grams divided by liters. So our solubility will be 0.70 grams divided by 1 liter. And then our pressure, it said it was at 1 atmosphere. So it's going to be divided by 1. And so our answer for the KH value will be 0.70. So that is our KH value. And now it says at different circumstances, at 4 atmospheres, how many grams can it dissolve in 1 liter of water? So since we're finding how many grams it can dissolve in 1 liter of water, it's asking for the solubility. And so we will set it up equal to solubility this time, using the same KH value we just calculated, the 0.70, and at 4 atmospheres times by 4, we will get a value of 2.80 grams per liter, because it is in solubility units, and because it was asking how many grams dissolve in 1 liter of water, we can just multiply this by 1 liter and it'll give us 2.80 grams still. So that is how much mass dissolved. So that is the answer to this problem. Sorry, kind of went over the notes there. But yeah, this problem is not as complicated as it sounds because it is using this equation just in different ways 2 times. Okay, let's work on the next problem here. It is problem 23, and it reads, the Henry's law constant for CO2 is 3.4 times 10 to the negative 2 molarity per atmosphere at 25 degrees Celsius. Assuming ideal solution behavior, what pressure of carbon dioxide is needed to maintain a CO2 concentration of 0.10 molarity in a can of lemon lime soda? So, first of all, we will be working with the same kind of problem that we just worked with here. So it's the solubility equals KH, the constant, times the pressure. So it already gives us the constant, which is KH, and then it gives us the molarity, so the moles per liter per atmosphere. So that is the KH value because this KH has to cancel out the pressure and solubility units, so that checks out. And so it's asking what pressure needs to be maintained at a concentration right here. And this is moles per liter, so that checks out for what we need to use for this problem. So we need to set it up equal to the pressure because that's what it's asking for. So P equals solubility divided by KH. And so the solubility here is going to be the 0.1, and then the KH value is going to be the 3.4 times 10 to the negative 2, and we will get a value of 2.94 atmospheres. And so that is how we solve for this one. And just to keep in mind, because the last problem when we were working with this, we were working with a solubility of grams per liter, and in this case, the KH value, the solubility units were in moles per liter. And the reason why that's okay that we didn't need grams per liter is because our constant was in molarity divided by pressure. So the molarity was moles per liter. So because the moles per liter canceled out with these two that we calculated, it's okay that we didn't need to convert it to grams per liter. If the constant was in grams per liter, then you would need to convert the solubility as well to make sure the units check out. Okay, so let's move on to 30. So 30 says, what are the mole fractions of H3PO4 and water in a solution of 14.5 grams of H3PO4 and 125 grams of water? So we first need to figure out the steps that we're going to write out for this problem. And to find the mole fractions, we need to find the moles of basically everything. So we have water and H3PO4. So we will first need to convert the grams of H3PO4 and water to moles. So convert both. And now number 2, we should combine moles just found for total mole amount. And so now number 3/4 divide H3PO4 by total moles, and vice versa with water. So water moles divided by total moles. And so now let's actually calculate all of that out. And so just to remind you, the equation for the mole fraction is going to be XA equal to mole of A, and mole of A is just any specific compound or atom that you're working with, divided by the mole total. And so we don't multiply this by 100 because we're not finding a percent. So this should be in decimals. So yeah, don't turn it into a percent value. That's not what a mole fraction is. So now let's answer the question. So like I was just saying, the first step is to convert the grams of H3PO4 and water to moles. So in the question, it has 14.5 grams of H3PO4. And now we'll use the molar mass to convert it to moles. And so the molar mass of H3PO4 is 97.9769 per 1 mole. And that will get us a value of 0.14799 moles of H3PO4. And then let's convert the water as well. So we have 125 grams of H2O. Actually, let me move this down really quick. And for every 1 mole of the water, we will have 18.02 grams. So that's the molar mass of water. And so calculated that out is 6.936737 moles of water. And so now the total moles, just adding those two together. And let's write that. Yeah, the total moles will equal 7.08473 moles. So those are the total moles. It's just adding these two values together, moles of water and H3PO4. And so now let's find the mole fractions. And I'm going to shrink this down so I can have you all see it better. Okay, so for XH3PO4, we had 0.147994068. I just added more decimal points just now, but you don't need to do that if it's already going on and on. Divided by the total moles, which is 7.08473. And so we will get a value of 0.0209. So that is the mole fraction of that one. So now let's do the same for water. We had 6.936737 divided by the total, 7.08473. And so now we will get a mole fraction value of 0.9791. So those are the mole fractions for water and H3PO4. Okay, so let's move on to the next problem. I'll leave that up for a second if you are still looking at that. So now we will work on problem 36. So it asks the question, what is the molality? So that's not the same as molarity. I sometimes get it confused myself. But what is the molality of phosphoric acid H3PO4, just as we were working with, in a solution of 14.5 grams of H3PO4 in 125 grams of water? So the equation for molality is going to be the moles of the solute divided by the kilograms, so the mass of the solvent. So it's not going to be divided by the solution, which is, if it's water, and in this case H3PO4, it would just be water because water is only the solvent here. So I'll write that off to the side right here. So molality equals moles solute divided by kilograms of solvent. Okay, so we will need to write out the steps necessary to answer this question. So number 1, we will need to convert grams of H3PO4 to moles. So we just did that in the last problem, but we'll go over it again really quickly, just in case you need more practice. And number 2, we need to convert the grams of water to kilograms, because specifically molality is in kilograms of solvent. And then number 3, divide moles H3PO4 by kilograms of water. And so that's using that equation right there in number 3. So now let's actually solve all of that out. And so just as we did before with finding grams to moles, we have 14.5 grams to start with. Using the molar mass, it's 97.9769 grams per 1 mole. And we'll be left with moles. And we will have 1.4799468 moles of H3PO4. And then the grams to kilograms of water, we started out with 125. And there are 1,000 grams for every 1 kilogram. And so we'll be left with kilograms as well. And we will have 0.125 kilograms of water. And so now all we have to do is divide those. And so M, so that's molality, the lowercase m, just as a quick note. Capital case M is molarity, and lowercase m is molality. It's just the same as like with specific heat and heat capacity. It's lowercase c and then capital C. So lowercase m equals the moles that we just calculated for of HCpO4 divided by the 0.125 kilograms. And so we will be left with the value of 1.18 moles per kilogram. And so that is how you calculate for the molality in this problem. So that is all I have for today. I'll leave this all up right here. I don't have any more problems. Let me know if you want to go over anything. I have around 10ish minutes to go over anything else you need to cover. But if there aren't any more questions, I'm going to end the stream for today. And as always, this will be posted to the PSU Learning Center's YouTube channel. And the textbook that I used is the free textbook, the Chemistry 2E OpenStax, I believe. So if you want that link as well, just let me know. But if not, that is all, and I will see you all next week.